Good day. In this video, we will continue the design of our graphical user interface. Okay, so we will now put computations or logics in our buttons and in our entry boxes. Okay, so let's go back to our Visual Studio Code in our mygui.py Python file. Okay, so let's put a logic in our reset button. Okay, so we will put the logic up here after the window and title commands. Okay, so we created first the design of our graphical user interface so that it will be easy for us to create variables for our computations or our logic uh, in our functions here in Visual Studio Code. Okay, so we will use the define function. We will define a function using this def package of Python or def feature of Python. So we will name this function reset close open parenthesis colon. Okay, so this will be the function we will call out if we will use the reset button. Okay, so under this reset function, okay, we will need the entry box variable, okay, from our variable one, a variable from our widget a1 underscore e entry box. Okay, so this is the variable a1 underscore e. Then to function as a reset code for a reset button, so we will use the delete close open parenthesis command. Then inside of it is 0, which means if we press the reset button, it will reset back to 0. Then we will also type end. End means there will nothing follows after we reset our entry boxes. So we will just wait for other commands or instruction from our code. So we will just copy this based on the number of our link lengths, and then edit their variables. So we have 4 link lengths. Next. So for our joint variable, so we have a T1, we have T2, and we have T3. Next, for our position vector, so X, Y, and Z. Okay. This is the logic of our reset button. To call out this function, we will go back to the RST or reset widget where the reset button is placed. Then, after the font color, we will add this command and the name of the function reset. So we will call out this function reset so that it will reset anything inside the entry box of our graphical user interface. So let's save this, Ctrl S. Okay, and let's go to our terminal and check if this is functioning. Let's close the graphical user interface first. Then paste. Excuse me. So let's test if this is reset button is functioning. So let's put some number. Okay, or put some number in our entry boxes. Then let's press reset. Okay, so it deletes and reset everything inside the entry box. So even we don't complete the entry boxes. Okay, let's let's reset them. Okay, so reset button is still functioning. Okay, so next let's put the calculation or the logic of our forward button. Okay, so to do that, we need our FKin.py Python file. Okay, for that for that for that next code, next set of codes. Okay, so we will make a new function. We will define new function. So we will name it f underscore k, close open parenthesis, then colon. So we will copy from our FKin.py Python file the link lengths, the code for link lengths. Okay, so let's make sure they are all indented. Okay, so link lengths should be centimeter in this graphical user interface, not in millimeter. Okay, so we will not use the input command. Instead, we will use another command. Okay, so that we can capture the what so that we will capture anything we insert in our entry box. Okay, so let's delete this because input command just works in the terminal. Okay, if we want to input something in our code, this input command will just function in our terminal. But because we are using a graphical user interface, okay, we will use other command. Okay, so we will use again the variable of our entry box. Then we'll use the .get close open parenthesis. Using the .get close open parenthesis, we will get or capture whatever we enter inside the entry box. Then we will not erase the float. Okay, the float method because we need sometimes we need to calculate decimal link lengths as well as joint variables. Okay, then because this is centimeter and we will use the robotics toolbox by Peter Corke, we will convert this into meter so that it will process inside our program as a meter. but we will need it to become centimeter again if we will display it in our graphical user interface. Okay, so from here we will already convert this into meter. So let's divide it to 100. Okay, and let's just copy this. Okay, let's copy paste this, then change the variables. Okay, this is A3, then this is A4. Okay, next is the joint variables. Okay, so let's make sure it is indented when we copy paste it. Okay, so let's copy this for our T1 because this is in centimeter also. Let's change the variable. Next, let's just copy the .get command and replace the input for our T2. Let's change this into T2. And this is T3. Okay. Next, we will need the degree to region conversion of T2 and T3. We need this because Python only identifies region. It doesn't identify rotation angles in degrees. Okay. Next is the parametric table. Okay, for the computation of our forward kinematics. Let's paste this. Then indent the PT. Okay. Let's align them. Next. Let's go back to our FKin.py. We will copy the HTM formula. Okay. For HTM formula, let's make sure it is indented. Okay. And align. Okay. Wait, something is missing. Okay. Next, from FKin.py again, let's copy our homogeneous transformation matrix variable with np.matrix. Next, and also the dot product variables. Okay, let's save this. Next, we will create new variable to extract the data of our position vector from our x03. So our position vector are the x, y, and z axis in our uh, mechanical manipulators base frame. Okay, so the value of the z sub 0, the x sub 0, and the y sub 0. Okay, it is where the end effector is located reference to or reference from the base. So in this homogeneous transformation matrix, we just need this. We just need this column. Okay, this is where the x-axis, y-axis, and the z-axis is located. Okay. Let's go back to our program. We will extract the we will create a new variable. It's x0 underscore 3. And it will be equals to h0 underscore 3. Then to extract the x axis, we will use this square parenthesis, then its element in the homogeneous transformation matrix, which is row 0, column 3. Okay. Then for y and z, okay, for y and z, this is y. The position of this y-axis is at element row 1, column 3, and the position of the z-axis is at row 2, column 3. Okay. So this will capture or extract the position vector data from our homogeneous transformation matrix x03. So to make this appear in our entry box of our position vector, we need another code. Okay. Under the x0 underscore 3 variable, x0 underscore 3 is the x underscore e, the variable of the entry box widget for the x-axis. Then we will use the command .insert. Okay. Close open parenthesis. Inside the close open parenthesis is 0, so it means the count will start at 0. We will round off the decimal answer of x0 underscore 3 into 3 decimal places. So x0 underscore 3, then 3 for the 3 decimal places. Then at this moment, we will convert again our answer into centimeter. So from meter to centimeter. So our input is in centimeter. We will process it inside in meter because of the robotics toolbox. Then the output is also will be converted into centimeter because centimeter is what we entered in our graphical user interface. So we will expect also an answer of we will also expect an answer in centimeter. Okay, so we will multiply this to 100. Okay, so we will copy this and paste for the y and z axis. Okay, so this is y, this is y, this is z, and this is z. Okay, so we will add another feature in our calculator. It is when we change the value of our link lengths or joint variables, we don't need to reset everything inside our entry boxes. Okay, so every time we compute, the answer before our new computation will be erased automatically. So we will use again another code for our variable x underscore e, the variable of our entry box. So we will use that delete. It's like it will erase the entry every time the entry in our entry box every time we change our values for the link lengths and joint variables. So it will again reset to 0, then end. So it will just wait what will happen next. Okay, so we will paste for y and z. So let's change the variable. Sorry, this is z. Okay, next. So to simulate our model inside, also inside our f underscore k function, is we will copy the link model, okay, the create link model from our model.py to our mygui.py. Okay, so let's make sure again it is indented. Okay, so we will change this, we will just remove this LM1 and change this to 30 centimeter. 30 centimeter will be the limit of the extension of our prismatic joint in our joint 1. Okay, so because this is centimeter, we will divide this into 100. Okay, to process it in a meter. Okay, but we will not convert it back to centimeter because the limit is not our concern. Okay, it's not yet our concern. Then instead of teaching the output, we will plot it. Unlike in model.py, we open a window to teach our mechanical manipulator. In this graphical user interface, we will plot as a simulation of our mechanical manipulator. So what we need in our plot first is the plot joints. The plot joints will be inside in a variable. Then at in this variable, an array, okay, an array of our joints. So we have three joint variables: the D1, the T2, and the T3. So we will use these three joint variables in our plot. Okay, plot of our simulation. We will add a 0 after T3, comma 0, because our link model consists of 4 links. Okay, the first link is a prismatic joint. The second link is a revolute joint. The third link is a revolute joint. This link is just a prismatic link. It means it doesn't extend. Okay, so this happens if your manipulator is a SCARA manipulator, or if your manipulator has a link that doesn't move, doesn't translate, or doesn't rotate. Okay, so we will need these flat joints. Next is the flat scale. Flat scale will be the scale of our 3D Cartesian coordinate system. So x sub 1 will be the lower limit of our x-axis. So let's just give it negative 0.5. For our x sub 2, we will give it 0.5. For y-axis y sub 1, this is our lower limit. Let's give a negative 0.5. For the upper limit, our y-axis, it will become 0.5. For the lower limit of our z-axis, let's make it 0.0, because 0.0 means the origin or the ground. Then lastly, z2 is equals to 0.5. So after this, the last code we will use for today's video, the plot command. Okay, we will use the variable of our link model SCARA v3. Okay, this is the name of our robot, or our mechanical manipulator SCARA v3. Then that plot. Okay, then close open parenthesis. Inside the close open parenthesis is the first the plot joints, which is Q1. Next, the plot scales. So we will put it inside the variable limits. Then it will be equal to a square parenthesis. Then inside that square parenthesis are the plot scales. So x1, x2, y1, y2, z1, and z2. After that, we will put this last command, which is block is equals to true. Okay, this means this just means that we don't want our plot or our simulation to close after we run this program. We want our plot to stay. Okay, to stay or not or not or stay or not just appear for a second. Okay, so let's save this and check it in our terminal. Okay. Oh, sorry, I forgot. I almost forgot. This will not work because we did not call out f underscore k. So this will work if we add the command in our fk widget. Okay, so this will be fk. This will be command is equals to f underscore k. So we need to call out our function f underscore k in our button. Okay, fk button. Okay, next, let's go back to our terminal. So this will work. Okay, Control V, Enter. Okay, so again, this is our graphical user interface. Let's check if it will work. So let's try 10, 15, 15, 15. Let's check first if the variables are 0. So let's press forward button. Okay, so this is how it works. Every time we press forward, it will compute the position vector. Then it will also show the simulation of our manipulator. So this is the simulation of the manipulator in a robotics toolbox. Let's change the add 10 or 10 again in T1. Let's make T2 negative 30 degrees, and let's make T3 45 degrees. Okay, let's press forward. Okay, so this is the plot or the simulation of our mechanical manipulator in robotics toolbox. So this is what our mechanical manipulator looks like in this position vector. Okay, this is where the end effector is located in x-axis, y-axis, and z-axis. If the joint variable is 10 centimeter, negative 30 degrees, and 45 degrees. Okay. So in next video, we will finish this by adding image in our graphical user interface and also checking if this is correct.